Welcome to our full guide to quantum mechanics, a journey into the very fabric of reality. In this video, we'll explore the fascinating world of quantum mechanics, a field that defies our everyday intuition and challenges our understanding of the universe. Quantum mechanics is the branch of physics that deals with the behavior of particles on the smallest scales, such as atoms and subatomic particles. It provides a mathematical framework for understanding and predicting the behavior of these tiny particles, which often behave in ways that seem counterintuitive. This guide will take you through the fundamental principles of quantum mechanics, starting with wave-particle duality, where particles exhibit both wave-like and particle-like properties. We'll delve into quantum superposition, where particles can exist in multiple states simultaneously, and quantum entanglement, a phenomenon that connects particles instantaneously, regardless of distance. We'll also cover the uncertainty principle, which limits the precision with which we can know certain pairs of properties about a particle, such as its position and momentum. And we'll explore the quantization of energy, the idea that energy levels in atoms are discrete rather than continuous. Next, we'll dive into the mathematical foundations necessary to understand quantum mechanics. This includes complex numbers, linear algebra, and probability theory. We'll introduce the Schrödinger equation, which describes how the quantum state of a physical system changes over time, and discuss operators and eigenvalues, which are key concepts in the mathematics of quantum mechanics. We'll then move on to quantum states, discussing wave functions, which describe the probability distribution of a particle's position. We'll explore Hilbert space, the mathematical space in which quantum states reside, and bracket notation, a convenient shorthand for describing quantum states. Additionally, we'll cover quantum state vectors and density matrices, tools for representing and analyzing quantum systems. Our journey continues with quantum dynamics, exploring the time-dependent Schrödinger equation and the Heisenberg picture, an alternative formulation of quantum mechanics. We'll discuss path integrals, a method for calculating the probability of a particle's path, and quantum tunneling, where particles pass through barriers they seemingly shouldn't be able to. We'll also touch on decoherence, the process by which quantum systems interact with their environment and lose their quantum behavior. Measurement in quantum mechanics is a critical topic, and we'll delve into the measurement postulates, which describe how measurements affect quantum systems. We'll discuss the collapse of the wave function, where a particle's state becomes definite upon measurement, and observables and expectation values, which represent measurable properties and their average values. The quantum Zeno effect and the measurement problem will also be covered. We'll explore various quantum systems, starting with single-particle systems and moving on to multi-particle systems. We'll discuss identical particles and symmetrization, the quantum harmonic oscillator, and spin systems, which have unique properties and applications. Wave-particle duality is a central concept in quantum mechanics. It describes how particles, such as electrons and photons, exhibit both wave-like and particle-like properties. This duality was first proposed by Louis de Broglie in 1924. He suggested that particles could behave as waves, which was a revolutionary idea at the time. Experiments such as the double-slit experiment provide compelling evidence for wave-particle duality. When particles pass through two slits, they create an interference pattern, characteristic of waves. However, if one observes which slit the particles go through, they behave like particles, not waves. This experiment shows that the act of measurement can influence the behavior of particles. Light is a well-known example of wave-particle duality. It can behave as an electromagnetic wave, but also as a stream of particles called photons. Electrons also exhibit wave-particle duality. They can create diffraction patterns, similar to light waves, when passed through a crystal or a series of slits. Wave-particle duality is not limited to light and electrons. It applies to all quantum particles, including atoms and molecules. This dual nature is described mathematically by the wave function. The wave function represents the probability amplitude of a particle's position and momentum. Max Planck's work on blackbody radiation laid the groundwork for wave-particle duality. He introduced the idea of quantized energy levels, which was crucial for developing quantum theory. Albert Einstein's explanation of the photoelectric effect provided further support. He showed that light must be quantized into photons to explain how it can knock electrons off a metal surface. The concept of wave-particle duality challenges our classical understanding of nature. In the macroscopic world, objects are either particles or waves, but in the quantum realm, they can be both. This duality is essential for technologies such as electron microscopes. These devices exploit the wave nature of electrons to achieve much higher resolutions than optical microscopes. Wave-particle duality also has implications for the nature of reality. It suggests that particles do not have definite properties until they are measured. Understanding wave-particle duality helps in grasping other quantum phenomena. Concepts like superposition and entanglement are deeply connected to the wave-like behavior of particles. The exploration of wave-particle duality continues to be an active area of research. It remains a profound and intriguing aspect of quantum mechanics, inviting deeper inquiry and understanding. Quantum superposition is a fundamental principle of quantum mechanics. It states that a quantum system can exist in multiple states simultaneously until it is measured. This principle was first articulated by Erwin Schrödinger. He illustrated it with his famous thought experiment involving a cat that is simultaneously alive and dead. In mathematical terms, superposition is described by a wave function. The wave function represents all possible states of a system at once. When a measurement is made, the wave function collapses. This collapse results in the system adopting one definite state. Superposition explains the behavior of particles in the double-slit experiment. Particles travel through both slits simultaneously, creating an interference pattern. This principle also underlies the concept of quantum bits, or qubits. In quantum computing, qubits can represent both 0 and 1 at the same time, vastly increasing computational power. Superposition leads to phenomena such as quantum interference. Particles in a superposition of states can interfere with themselves, leading to unique and unexpected results. In chemistry, superposition explains the behavior of electrons in atoms. Electrons exist in a superposition of all possible orbitals until they are observed. Superposition also plays a crucial role in quantum entanglement. Entangled particles remain in a superposition of states that are correlated with each other, no matter the distance between them. The principle of superposition challenges classical intuition. In the macroscopic world, objects are either in one state or another, but quantum systems can be in multiple states at once. Experimental verification of superposition comes from tests on small particles. These experiments consistently show that particles can exist in multiple states until measured. The principle of superposition is integral to many quantum technologies. Quantum sensors, for example, exploit superposition to measure physical quantities with high precision. Quantum superposition is also crucial for understanding quantum decoherence. Decoherence describes how quantum systems lose their superposition states through interaction with their environment. Researchers continue to explore superposition in various systems. The ongoing study of superposition helps to deepen our understanding of quantum mechanics and its applications. The principle of quantum superposition remains a cornerstone of quantum theory. It opens up a world of possibilities and challenges our understanding of reality. Quantum entanglement is one of the most intriguing phenomena in quantum mechanics. It occurs when particles become interconnected, and the state of one instantly influences the state of another, regardless of the distance between them. Albert Einstein famously referred to entanglement as spooky action at a distance. This is because entangled particles seem to communicate instantaneously, defying the classical notion of locality. The concept of entanglement was first explored in the EPR paradox, named after Einstein, Podolsky, and Rosen. They questioned whether quantum mechanics could be a complete theory, given the strange implications of entanglement. John Bell later formulated Bell's theorem to test the predictions of quantum mechanics against local hidden variable theories. Experiments testing Bell's inequalities have consistently supported the predictions of quantum mechanics, confirming the reality of entanglement. Entanglement is a key resource in quantum computing and quantum cryptography. It enables protocols like quantum teleportation, where the state of a particle can be transmitted instantaneously to another particle far away. In quantum computing, entangled qubits can perform complex calculations much more efficiently than classical bits. This is because the entanglement allows qubits to represent and process multiple states simultaneously. Quantum entanglement also plays a role in quantum key distribution. It ensures secure communication by detecting any eavesdropping attempts, as measuring an entangled particle affects its partner instantly. Experimental verification of entanglement involves creating pairs of entangled particles and measuring their states. These experiments have been performed with photons, electrons, and even larger molecules. The phenomenon of entanglement has profound implications for our understanding of reality. It challenges the classical idea that objects have definite states independent of observation, and raises questions about the nature of information. Entanglement suggests that the universe is fundamentally interconnected. This interconnectedness is not limited by the speed of light, as changes in one part of an entangled system are reflected instantaneously in the other. Research into entanglement continues to push the boundaries of quantum mechanics. Scientists are exploring how entanglement can be harnessed for new technologies and deeper insights into the nature of the universe. Entangled states are delicate and can be easily disrupted by their environment, a process known as decoherence. Understanding and mitigating decoherence is crucial for developing practical quantum technologies. Entanglement has been demonstrated over increasingly large distances. Experiments have shown entanglement between particles separated by kilometers, and efforts are underway to achieve even greater distances. The study of entanglement intersects with various fields, including quantum information theory, condensed matter physics, and cosmology. It remains a vibrant area of research with many open questions and potential applications. Quantum entanglement continues to captivate scientists and the public alike. Its mysterious nature and profound implications ensure it will remain a central topic in the ongoing exploration of quantum mechanics. The uncertainty principle is a fundamental concept in quantum mechanics. It was formulated by Werner Heisenberg in 1927 and states that it is impossible to simultaneously know both the exact position and exact momentum of a particle. This principle is not due to experimental limitations, but is intrinsic to the nature of quantum systems. The more precisely one property is measured, the less precisely the other can be known. Mathematically, the uncertainty principle is expressed as an inequality. It shows that the product of the uncertainties in position and momentum is always greater than or equal to a constant value, given by Planck's constant divided by 4p. The uncertainty principle implies that there is a fundamental limit to what can be known about a quantum system. This challenges classical physics, where it was assumed that particles could have well-defined positions and momenta. In everyday terms, the uncertainty principle means that at very small scales, particles do not have definite positions or momenta. Instead, they are described by a range of probable values. This principle has profound implications for our understanding of reality. It suggests that on a fundamental level, nature is inherently probabilistic rather than deterministic. The uncertainty principle is closely related to the concept of wave-particle duality. The wave-like nature of particles leads to uncertainty in their position and momentum. In quantum mechanics, particles are described by wave functions. The spread of the wave function determines the uncertainties in the particle's position and momentum. The uncertainty principle also affects energy and time. There is an analogous uncertainty relation between the energy of a system and the time over which it is measured. This energy-time uncertainty relation explains phenomena like quantum tunneling. Particles can temporarily borrow energy to pass through barriers, a process that would be forbidden in classical physics. The uncertainty principle is a cornerstone of quantum mechanics. It underlies many other quantum phenomena and is essential for understanding the behavior of quantum systems. It also has practical implications for technology. For example, it sets limits on the precision of measurements in quantum systems, affecting the design of quantum sensors and clocks. Heisenberg's uncertainty principle has been experimentally verified in numerous ways. These experiments consistently show that the uncertainty and momentum are inversely related, as predicted by the principle. The uncertainty principle challenges our classical intuitions about measurement and reality. It forces us to rethink concepts like determinism and the nature of physical laws. Research continues into the implications and applications of the uncertainty principle. It remains a vital area of study in the quest to understand the quantum world. Quantization of energy is a key concept in quantum mechanics. It refers to the idea that energy can only exist in discrete levels or quanta rather than a continuous range. This concept was first introduced by Max Planck in 1900. He proposed that the energy of electromagnetic waves is quantized to explain blackbody radiation. Albert Einstein extended this idea to light, suggesting that light consists of discrete packets called photons. Each photon carries a specific amount of energy determined by its frequency. In atoms, electrons occupy quantized energy levels. They can jump between these levels by absorbing or emitting photons, with the exact energy difference between levels. The quantization of energy explains the stability of atoms. Electrons remain in their quantized orbits, unless they gain or lose the precise amount of energy needed to move to a different level. This principle also explains atomic spectra. When electrons transition between energy levels, they emit or absorb light at specific frequencies, producing characteristic spectral lines. The quantization of energy is crucial for understanding chemical bonds. Electrons in molecules occupy quantized orbitals, determining the structure and properties of the molecules. In solids, the concept of energy bands arises from quantization. Electrons can occupy discrete energy bands, which explains the electrical properties of conductors, insulators, and semiconductors. Quantization is not limited to electrons and photons. Vibrations in molecules and crystals are also quantized, leading to discrete vibrational energy levels and phonons. The concept of quantized energy is essential for quantum field theory. Fields, such as the electromagnetic field, are quantized, with particles representing the quanta of these fields. Quantization also applies to angular momentum. In quantum mechanics, angular momentum is quantized, with particles having discrete values of spin and orbital angular momentum. The quantization of energy has profound implications for technology. It underlies the operation of lasers, which rely on the stimulated emission of quantized photons. Quantum dots and other nanostructures exploit quantized energy levels to create devices with unique optical and electronic properties. These technologies have applications in computing, imaging, and medicine. The quantization of energy helps explain phenomena that classical physics cannot. For instance, it accounts for the specific heat capacities of solids and the behavior of electrons in superconductors. This concept continues to be a fundamental aspect of modern physics. Ongoing research into quantized systems reveals new insights and applications, pushing the boundaries of our technological capabilities. Wave functions are fundamental to quantum mechanics. They describe the quantum state of a system and contain all the information about that system's properties. The wave function is typically denoted by the Greek letter psi. It is a complex-valued function of space and time, representing the probability amplitude of a particle's position and momentum. The square of the wave function's magnitude gives the probability density. This tells us the likelihood of finding a particle in a particular location at a given time. Wave functions can interfere with each other. This interference leads to phenomena like diffraction and the formation of interference patterns in the double-slit experiment. Wave functions must satisfy certain conditions. They need to be normalized, meaning the total probability of finding the particle anywhere in space is 1. In one dimension, the Schrödinger equation governs the behavior of the wave function. It describes how the wave function evolves over time under the influence of potential energy. For bound systems like electrons in an atom, wave functions take the form of standing waves. These standing waves correspond to discrete energy levels, reflecting the quantization of energy. The nodes of a wave function are points where the probability density is 0. In higher energy states, wave functions have more nodes, corresponding to higher energy levels. Wave functions can also describe systems of multiple particles. In such cases, they depend on the coordinates of all the particles and encapsulate the correlations between them. When dealing with identical particles, wave functions must be symmetric or antisymmetric. Bosons have symmetric wave functions, while fermions have antisymmetric ones, leading to the Pauli exclusion principle. Superposition of wave functions is a key concept. A system can be described by a combination of multiple wave functions, leading to new and complex behaviors. Wave functions are not directly observable. Instead, we infer their properties through measurements, which collapse the wave function to a specific state. In quantum mechanics, the phase of a wave function is also important. Relative phases between different parts of a wave function can lead to constructive or destructive interference. Wave functions can be transformed using operators. Operators corresponding to physical quantities like momentum and energy act on wave functions to give eigenvalues, representing possible measurement outcomes. Understanding wave functions is crucial for predicting and explaining the behavior of quantum systems. They form the backbone of many quantum mechanical models and applications, from atoms to molecules and beyond. Hilbert space is a central concept in quantum mechanics. It provides the mathematical framework for describing quantum states and their evolution. A Hilbert space is a complete vector space with an inner product. This structure allows for the rigorous definition of distance and angle between vectors, representing quantum states. Quantum states in Hilbert space are represented by vectors, often called state vectors. These vectors encapsulate all possible information about a quantum system. The inner product in Hilbert space gives the probability amplitude. The square of this amplitude gives the probability of transitioning from one state to another. Operators in Hilbert space act on state vectors. These operators correspond to physical observables like position, momentum, and energy. Eigenvalues and eigenvectors of an operator have special significance. The eigenvalues represent possible measurement outcomes, while the eigenvectors represent the corresponding quantum states. Superposition of states is naturally described in Hilbert space. A quantum state can be expressed as a linear combination of basis vectors in the space. Orthogonality of vectors in Hilbert space is crucial. Orthogonal vectors represent mutually exclusive quantum states, with an inner product of zero. Hilbert space can have infinite dimensions. For example, the space of possible wave functions for a particle in a box is infinite dimensional. The completeness of Hilbert space ensures that every possible quantum state can be represented. This means that any wave function can be expressed as a sum of basis vectors. Unitary operators in Hilbert space describe the time evolution of quantum states. These operators preserve the inner product, ensuring the total probability remains 1. Projectors are special operators in Hilbert space. They project state vectors onto subspaces, representing measurement processes in quantum mechanics. Hilbert space also supports the concept of entanglement. Entangled states are described by vectors in a composite Hilbert space, formed by the tensor product of individual spaces. In quantum field theory, fields are quantized in Hilbert space. Each point in space-time corresponds to a different dimension in this infinite dimensional space. Understanding Hilbert space is essential for mastering quantum mechanics. It provides the mathematical backbone for the theory, enabling precise descriptions and predictions of quantum phenomena. Measurement postulates are fundamental to quantum mechanics. They describe how observations affect quantum systems and determine the outcomes of measurements. The first postulate states that physical quantities are represented by operators. These operators act on the wave functions of quantum systems. The second postulate involves eigenvalues and eigenstates. When a measurement is made, the system collapses to one of the operator's eigenstates, and the measurement yields the corresponding eigenvalue. The probability of measuring a particular eigenvalue is given by the square of the amplitude. This amplitude is the projection of the wave function onto the eigenstate. Measurement causes the wave function to collapse. Before measurement, a quantum system can be in a superposition of states. After measurement, it is in a single state. The collapse of the wave function is a key feature of quantum mechanics. It signifies the transition from quantum superposition to a definite state. The measurement postulates explain the discrete nature of quantum measurements. Unlike classical measurements, which can yield a continuous range of values, quantum measurements produce specific eigenvalues. These postulates are essential for predicting experimental outcomes. They allow physicists to calculate the probabilities of different results from quantum experiments. In quantum mechanics, measurements are probabilistic. The outcome of a measurement is not deterministic but has a probability distribution determined by the wave function. The measurement postulates also apply to composite systems. When measuring part of an entangled system, the entire system's wave function collapses accordingly. In practice, measurement can be described using projection operators. These operators project the wave function onto the eigenstate corresponding to the measurement result. Quantum measurements can be indirect or weak. Weak measurements provide partial information without fully collapsing the wave function, allowing for more nuanced observations. The measurement problem remains a topic of debate. It raises questions about the nature of reality and the role of the observer in quantum mechanics. The postulates highlight the difference between quantum and classical physics. In classical physics, measurements do not affect the system being measured, while in quantum mechanics, they fundamentally alter it. Understanding measurement postulates is crucial for grasping quantum mechanics. They are key to interpreting quantum experiments and understanding the behavior of quantum systems. The collapse of the wave function is a fundamental concept in quantum mechanics. It describes the change in a quantum system when a measurement is made. Before measurement, a quantum system exists in a superposition of states. This superposition represents all possible outcomes of a measurement. When a measurement occurs, the wave function collapses to a single state. This collapse corresponds to one of the possible outcomes. The collapse is instantaneous and non-deterministic. The specific outcome is probabilistic, determined by the wave function's amplitude for each possible state. This process is central to the Copenhagen interpretation of quantum mechanics. It suggests that physical systems do not have definite properties until they are measured. The concept of wave function collapse helps explain the results of quantum experiments. It accounts for the transition from a superposition to a definite measurement outcome. The collapse raises questions about the nature of reality. It implies that the act of measurement plays a crucial role in determining the state of a quantum system. There are various interpretations of wave function collapse. Some propose that collapse is a real physical process, while others view it as a change in our knowledge of the system. The many worlds interpretation avoids collapse by suggesting that all possible outcomes occur in separate, parallel universes. In this view, the wave function never collapses. The collapse of the wave function is linked to the observer effect. The act of observation or measurement affects the system being observed, making it behave differently. Experimental evidence supports the collapse concept. Experiments like the double-slit experiment show that measurement alters the behavior of quantum particles. The nature of wave function collapse is still a subject of debate. Researchers continue to explore its implications for the foundations of quantum mechanics. Understanding wave function collapse is crucial for interpreting quantum mechanics. It provides a framework for predicting the outcomes of measurements on quantum systems. The collapse process also has practical implications. It affects the design and operation of quantum technologies, such as quantum computers and sensors. Wave function collapse remains one of the most intriguing aspects of quantum mechanics. It challenges our understanding of measurement, reality, and the role of the observer in the quantum world. Observables are physical quantities in a quantum system that can be measured. They are represented by operators acting on the system's wave function. The expectation value of an observable provides the average outcome of many measurements. It is calculated using the wave function and the corresponding operator. Mathematically, the expectation value is the inner product of the wave function with the operator applied to the wave function. This gives a real number, even though the wave function itself is complex. Expectation values are crucial for linking quantum theory with experimental results. They allow us to predict the average behavior of a quantum system. For example, the expectation value of position gives the average position of a particle. Similarly, the expectation value of momentum gives the average momentum. In a measurement, the actual result might differ from the expectation value. However, over many measurements, the average will approach the expectation value. Operators corresponding to observables have eigenvalues and eigenstates. Measurements yield one of these eigenvalues, and the system collapses into the corresponding eigenstate. The expectation value can be seen as a weighted average of the eigenvalues. The weights are given by the probabilities of the system being in each eigenstate. Observables in quantum mechanics can include quantities like energy, spin, and angular momentum. Each has a corresponding operator with a set of eigenvalues and eigenstates. The Heisenberg uncertainty principle relates to observables. It states that certain pairs of observables, like position and momentum, cannot both have precise values simultaneously. In quantum mechanics, observables do not necessarily commute. The order in which measurements are made can affect the results, leading to uncertainty. Expectation values are essential for the equations of motion in quantum mechanics. They appear in formulations like the Ehrenfest theorem, which connects quantum and classical mechanics. The concept of expectation values extends to mixed states. In such cases, the density matrix formalism is used to calculate the expectation values. Understanding observables and expectation values is fundamental for quantum mechanics. They provide a bridge between the abstract formalism and tangible experimental predictions. These concepts are also crucial for developing quantum technologies. Accurate predictions of expectation values are essential for designing and interpreting experiments in quantum computing and other fields. The quantum Zeno effect is a phenomenon where frequent measurements prevent a quantum system from evolving. It is named after Zeno's paradoxes in classical philosophy. In quantum mechanics, measurements disturb the system, causing it to collapse into a particular state. When measurements are made frequently enough, they can effectively freeze the system in its initial state. This effect is a consequence of the wave function collapse. Each measurement resets the evolution of the wave function, preventing it from developing naturally. The quantum Zeno effect can be demonstrated in various experiments. For instance, repeatedly observing an unstable particle can delay its decay. The effect has implications for quantum control and computation. It suggests that by carefully timing measurements, we can influence and stabilize quantum states. Mathematically, the quantum Zeno effect is related to the time evolution of the wave function. Frequent measurements alter the system's evolution, reducing the probability of transition to other states. This effect also highlights the role of the observer in quantum mechanics. It demonstrates how the act of measurement can significantly impact the behavior of quantum systems. In addition to delaying decay, the quantum Zeno effect can prevent transitions between energy levels. This has potential applications in controlling atomic and molecular states. The quantum Zeno effect can be contrasted with the anti-Zeno effect. In the anti-Zeno effect, frequent measurements can accelerate the system's evolution rather than inhibiting it. Experimental verification of the quantum Zeno effect has been achieved in various systems, including trapped ions and cold atoms. These experiments confirm that frequent observations can indeed inhibit quantum transitions. Understanding the quantum Zeno effect is important for interpreting quantum measurements. It shows how the timing and frequency of observations can influence the outcome of experiments. The effect also has implications for decoherence and quantum information. It suggests ways to protect quantum information from decoherence by using frequent measurements. The quantum Zeno effect is a striking example of quantum mechanics' counterintuitive nature. It challenges our classical intuitions about time, observation, and change. Ongoing research explores new ways to harness the quantum Zeno effect. This includes potential applications in quantum computing, where controlling quantum states is crucial. The study of the quantum Zeno effect continues to reveal deeper insights into the nature of quantum measurements. It remains a fascinating topic in the broader understanding of quantum dynamics. The measurement problem is a fundamental issue in quantum mechanics. It concerns the question of how and why observations cause wave function collapse. In quantum mechanics, systems exist in a superposition of states until measured. The measurement problem asks, what precisely causes the collapse to a single outcome? There are several interpretations of quantum mechanics that address the measurement problem. Each offers a different perspective on the nature of reality and the role of the observer. The Copenhagen interpretation posits that the act of measurement causes collapse. This interpretation, however, leaves open the question of what constitutes a measurement. The many worlds interpretation suggests that all possible outcomes of a measurement occur in separate branching universes. In this view, there is no actual collapse. The objective collapse theories propose that wave function collapse is a physical process. This could be triggered by interactions with the environment or other mechanisms. Decoherence theory provides another angle. It explains how interactions with the environment cause superpositions to appear as mixed states, though it doesn't solve the problem of definite outcomes. The measurement problem also ties into the concept of observer effect. It raises questions about whether the observer's consciousness plays a role in wave function collapse. Quantum mechanics does not specify when or how a measurement collapses the wave function. This ambiguity is at the heart of the measurement problem. Schrödinger's cat paradox illustrates the measurement problem. The cat in the box is both alive and dead until observed, highlighting the strangeness of superposition and collapse. Hidden variable theories attempt to provide a deterministic solution. They suggest that underlying variables determine outcomes, but these are not part of standard quantum mechanics. Bohmian mechanics is one such theory. It introduces hidden variables that guide particles, offering a deterministic view that sidesteps the measurement problem. Experiments continue to probe the nature of wave function collapse. These include tests of Bell's inequalities, which challenge local hidden variable theories. Understanding the measurement problem is crucial for the foundations of quantum mechanics. It influences our interpretation of quantum theory and its implications for reality. The debate over the measurement problem drives ongoing research. Physicists and philosophers alike seek a clearer understanding of how measurements affect quantum systems. Resolving the measurement problem could have profound implications. It might redefine our understanding of quantum mechanics and the nature of observation itself. Single particle systems are the simplest quantum systems to study. They provide fundamental insights into quantum mechanics and its principles. In a single particle system, the wave function describes the probability distribution of the particle's position and momentum. The Schrödinger equation governs the evolution of this wave function over time. One classic example is the particle in a box. The particle is confined to a finite region, and its wave function must satisfy boundary conditions, leading to quantized energy levels. The harmonic oscillator is another key example. It models a particle in a potential well, such as an atom in a crystal lattice, and exhibits discrete energy levels and characteristic wave functions. The free particle system has no potential, allowing the particle to move freely. Its wave function is typically a plane wave, representing constant momentum. The hydrogen atom is a more complex single particle system. It consists of an electron bound to a proton by the Coulomb potential, leading to quantized energy levels and specific orbital shapes. In quantum mechanics, single particle systems can be described in different potential fields. These fields determine the shape and behavior of the wave functions and energy spectra. Scattering problems are another area of study. They involve a particle encountering a potential barrier or well, with solutions describing reflection and transmission probabilities. Single particle systems also include spin. Spin is an intrinsic form of angular momentum, adding another layer of complexity to the system's quantum state. The study of single particle systems lays the groundwork for understanding more complex systems. Many body systems, for instance, build upon the principles learned from single particles. These systems can be solved exactly in some cases. Exact solutions provide benchmarks for approximations and numerical methods used in more complex scenarios. Single particle quantum systems are essential for developing quantum technologies. Understanding their behavior is crucial for designing quantum sensors, computers, and communication devices. They also provide insight into fundamental physics. Studies of single particle systems have led to discoveries such as the quantization of energy and the dual nature of particles. Experiments with single particle systems help validate quantum theory. Techniques like atomic traps and quantum dots allow precise control and measurement of individual particles. Research on single particle systems continues to be a vibrant field. It provides ongoing opportunities to refine our understanding of quantum mechanics and explore new quantum phenomena. Multi-particle systems involve interactions between multiple quantum particles. These systems exhibit complex behaviors that arise from the principles of quantum mechanics. In a multi-particle system, each particle is described by its own wave function. The total wave function of the system is a combination of the individual wave functions. One key concept in multi-particle systems is entanglement. When particles become entangled, the state of one particle is dependent on the state of another, no matter the distance between them. Multi-particle systems can be fermions or bosons. Fermions, such as electrons, obey the Pauli exclusion principle, while bosons, like photons, do not. The Pauli exclusion principle states that no two fermions can occupy the same quantum state simultaneously. This principle is crucial for the structure of atoms and the stability of matter. In bosonic systems, particles can occupy the same state. This leads to phenomena such as Bose-Einstein condensation, where particles condense into the same ground state at low temperatures. The study of multiparticle systems often involves the use of second quantization. This formalism simplifies the treatment of many particle states and interactions. Interactions between particles are typically described by potential functions. These potentials determine how particles influence each other's behavior and energy levels. One important example of a multiparticle system is the helium atom. It consists of two electrons interacting with each other and the nucleus, requiring complex wave functions to describe. Multiparticle systems can also form solids and liquids. The interactions between vast numbers of atoms and molecules lead to the macroscopic properties of these states of matter.
Quantum statistics play a crucial role in Fermi-Dirac statistics apply to fermions, while Bose-Einstein statistics apply to bosons, influencing their collective behavior.
These systems are essential for understanding superconductivity. In superconductors, pairs of electrons called Cooper pairs move without resistance, a phenomenon arising from quantum mechanics. Multi-particle quantum systems are also studied in quantum chemistry. The behavior of electrons in molecules determines chemical bonding and reactions, critical for understanding chemistry. Quantum simulations of multiparticle systems help explore new materials. These simulations can predict the properties of materials before they are synthesized in the lab. Research on multiparticle systems continues to advance our understanding of the quantum world. These studies have implications for physics, chemistry, materials science, and beyond. Identical particles are particles that cannot be distinguished from one another, even in principle. This indistinguishability leads to unique quantum statistical behaviors. Symmetrization is a key concept when dealing with identical particles. It involves ensuring that the wave function of the system reflects the indistinguishable nature of the particles. For bosons, the wave function must be symmetric. This means that exchanging two particles does not change the wave function, reflecting their ability to occupy the same state. For fermions, the wave function must be antisymmetric. Exchanging two fermions changes the sign of the wave function, which leads to the Pauli exclusion principle. Symmetrization has significant consequences for the properties of quantum systems. It dictates the statistical distribution that particles follow and affects the overall behavior of the system. In the case of fermions, antisymmetry leads to Fermi-Dirac statistics. These statistics are crucial for understanding the electronic structure of atoms and the behavior of electrons in solids. For bosons, symmetry leads to Bose-Einstein statistics. These statistics explain phenomena like Bose-Einstein condensation, where particles accumulate in the lowest energy state at low temperatures. Identical particles are often found in systems like atomic nuclei, where protons and neutrons are treated as identical fermions. Symmetrization plays a critical role in nuclear structure and reactions. In quantum field theory, particles like photons and electrons are also considered identical. This framework extends symmetrization principles to fields and their excitations. Symmetrization affects scattering experiments. Identical particles exhibit different interference patterns compared to distinguishable particles, impacting the outcomes of these experiments. Quantum entanglement in identical particle systems can exhibit unique properties. The indistinguishability of particles influences the nature and strength of their entanglement. In condensed matter physics, symmetrization principles are essential for understanding phenomena like superconductivity and superfluidity, where collective behaviors of identical particles dominate. Symmetrization also applies to molecular systems. Electrons in molecules must be treated as identical fermions, influencing chemical bonding and reactivity. Experimental techniques can exploit symmetrization effects. For instance, using identical photons in quantum optics experiments can enhance precision measurements and quantum information processing. Understanding symmetrization and the behavior of identical particles is crucial for advancing quantum theory. It provides deep insights into the fundamental nature of particles and their interactions, influencing various fields of physics. The quantum harmonic oscillator is a fundamental model in quantum mechanics. It describes a particle subject to a restoring force proportional to its displacement from equilibrium. This model is analogous to a mass on a spring in classical mechanics, However, in the quantum version, the energy levels are quantized. The energy levels of a quantum harmonic oscillator are equally spaced. This spacing is determined by the oscillator's frequency and Planck's constant. The wave functions of the quantum harmonic oscillator are described by Hermite polynomials. These wave functions represent the probability distributions of the particle's position. The ground state of the harmonic oscillator has the lowest possible energy. Even in this state, the particle has non-zero energy known as zero-point energy. Excited states of the oscillator correspond to higher energy levels. Each state has a distinct wave function with a specific number of nodes. The quantum harmonic oscillator is used to model vibrations in molecules. Each vibrational mode of a molecule can be approximated as a harmonic oscillator. In solids, the vibrations of atoms around their equilibrium positions can be described by harmonic oscillators. This is the basis for understanding phonons, the quanta of lattice vibrations. The quantum harmonic oscillator also provides insights into the behavior of quantum fields. Each mode of a quantum field can be treated as an independent harmonic oscillator. In the study of quantum optics, the electromagnetic field in a cavity can be modeled as a set of harmonic oscillators. This leads to the concept of quantized light modes. The simple mathematical form of the harmonic oscillator makes it a valuable teaching tool. It helps students understand the principles of quantization and wave functions. In quantum chemistry, the harmonic oscillator model is used to approximate the potential energy surfaces of molecules. This approximation simplifies the calculation of molecular vibrational spectra. The ladder operators are a key feature of the quantum harmonic oscillator. These operators allow transitions between energy levels, facilitating the analysis of the system's properties. The coherent states of the harmonic oscillator have unique properties. They minimize the uncertainty in position and momentum, resembling classical states more closely than other quantum states. The quantum harmonic oscillator remains a cornerstone of quantum mechanics. Its principles are applied in various fields, providing a deep understanding of both fundamental and applied quantum phenomena. Spin systems are an essential aspect of quantum mechanics. Spin is an intrinsic form of angular momentum carried by quantum particles. Each particle has a specific spin quantum number. For example, electrons have a spin of 1/2, while photons have a spin of 1. Spin states can be represented by spinors. For a spin 1/2 particle, there are two possible spin states, spin up and spin down. The behavior of spin in a magnetic field is described by the Zeeman effect. The magnetic field splits the energy levels of the spin states, leading to distinct energy separations. Spin systems are fundamental to the operation of magnetic resonance imaging. MRI technology exploits the alignment of nuclear spins in a magnetic field to produce detailed images of the body. In quantum computing, spin systems are used to represent qubits. The two spin states of a particle can encode the binary information necessary for quantum computation. Entanglement in spin systems plays a crucial role in quantum information. Entangled spins can be used to perform tasks like quantum teleportation and superdense coding. The study of spin systems extends to condensed matter physics. The interactions between spins in a material can lead to various magnetic properties, such as ferromagnetism and antiferromagnetism. Spintronics is a field that explores the use of electron spin in electronic devices. Spin-based electronics have the potential to be faster and more efficient than traditional charge-based electronics. In particle physics, spin is a key property that distinguishes different particles. The classification of particles into fermions and bosons is based on their spin. The Stern-Gerlach experiment was a pivotal demonstration of spin quantization. It showed that particles like electrons have discrete spin states when passed through a magnetic field gradient. Spin systems also exhibit quantum tunneling. Spin tunneling has implications for understanding molecular magnets and the behavior of spins in nanostructures. Manipulating spin systems requires precise control of external fields. Techniques like electron spin resonance and nuclear magnetic resonance are used to study and control spin dynamics. In many body physics, spin models like the Heisenberg model and the Ising model are used to understand collective behavior. These models help explain phase transitions and critical phenomena in spin systems. Research in spin systems continues to reveal new insights. Advances in this field are driving developments in quantum technology, material science, and our understanding of fundamental physics. Quantum computing harnesses the principles of quantum mechanics to process information. Unlike classical computers, which use bits, quantum computers use qubits. Qubits can exist in superposition, representing both 0 and 1 simultaneously. This allows quantum computers to perform many calculations at once. Entanglement is another crucial feature of quantum computing. Entangled qubits are linked, so the state of one instantly influences the state of another, regardless of distance. Quantum gates manipulate qubits through operations that change their state. These gates are the building blocks of quantum circuits, similar to logic gates in classical computing. Quantum algorithms leverage superposition and entanglement to solve problems more efficiently. Algorithms like Shor's algorithm can factor large numbers exponentially faster than classical methods. Quantum computers have the potential to revolutionize fields like cryptography. They could break widely used encryption schemes, necessitating the development of quantum-resistant encryption. Simulating quantum systems is a natural application for quantum computers. They can model complex molecular structures and interactions, aiding in drug discovery and materials science. Quantum error correction is essential for reliable quantum computing. It involves encoding information in a way that allows the system to detect and correct errors without measuring the qubits directly. Quantum supremacy refers to the point at which a quantum computer can perform a task beyond the capability of the best classical supercomputers. Achieving this milestone demonstrates the practical power of quantum computing. Building a scalable quantum computer is a significant challenge. It requires maintaining qubit coherence and minimizing errors in quantum operations. Several physical systems are being explored for qubit implementation. These include superconducting circuits, trapped ions, and topological qubits, each with its advantages and challenges. Quantum computing also impacts optimization problems. Quantum annealing and other quantum optimization techniques can potentially solve complex problems more efficiently than classical algorithms. Research in quantum computing is highly interdisciplinary. It involves physics, computer science, engineering, and mathematics, driving advances across these fields. Quantum networks are an emerging area of research. They aim to connect quantum computers, enabling distributed quantum computing and secure quantum communication. The future of quantum computing holds immense promise. As technology progresses, quantum computers are expected to tackle problems currently beyond our reach, transforming industries and scientific research. Quantum cryptography uses the principles of quantum mechanics to secure information. It offers theoretically unbreakable encryption based on the laws of physics. The most well-known quantum cryptographic method is quantum key distribution, or QKD. QKD allows two parties to generate a shared secret key, which can then be used for secure communication. One of the key protocols in QKD is the BB84 protocol. It uses the polarization states of photons to encode information, ensuring security through the principles of quantum mechanics. In QKD, any attempt to eavesdrop on the key distribution introduces detectable disturbances. This is due to the no-cloning theorem and the uncertainty principle, which prevent copying and precise measurement of quantum states. Quantum cryptography also includes quantum-secure direct communication. This method allows direct transmission of messages with built-in security measures. The security of quantum cryptography does not rely on computational hardness. Unlike classical cryptography, which can be compromised by powerful computers, quantum cryptography remains secure due to the fundamental nature of quantum mechanics. Implementing QKD requires a reliable source of entangled photons or single-photon emitters. Advances in photonics and quantum optics are crucial for the development of practical QKD systems. Quantum repeaters are necessary for long-distance QKD. They help maintain the integrity of the quantum signal over extended distances by overcoming the limitations of direct transmission. Quantum cryptography can secure various types of communication. It has potential applications in financial transactions, military communications, and critical infrastructure protection. Researchers are exploring integrating QKD with existing communication networks. This integration aims to enhance the security of traditional networks by adding a layer of quantum encryption. Quantum random number generators are another aspect of quantum cryptography. They use quantum processes to produce truly random numbers, essential for cryptographic applications. The development of quantum cryptography involves interdisciplinary efforts. It requires expertise in quantum mechanics, computer science, engineering, and information theory. Quantum cryptography also faces challenges. These include technical issues like photon loss and detector efficiency, as well as practical considerations like cost and scalability. International collaborations and standardization efforts are underway to advance quantum cryptography. These efforts aim to ensure compatibility and interoperability of quantum cryptographic systems. The future of quantum cryptography promises enhanced security for digital communications. As technology progresses, it is expected to play a critical role in protecting information in an increasingly connected world. Quantum teleportation is a process by which the state of a quantum system is transmitted from one location to another, without moving the physical system itself. This relies on the phenomenon of quantum entanglement. Entanglement creates a pair of particles with linked states, no matter the distance between them. When one particle of an entangled pair is measured, the state of the other instantaneously adjusts to reflect this measurement. In quantum teleportation, the sender and receiver share an entangled pair of particles. The sender performs a specific operation on their particle and the particle they wish to teleport, collapsing the state of the entangled pair. The result of this measurement is then sent to the receiver via classical communication. Using this information, the receiver applies a corresponding operation to their particle, recreating the original quantum state. Quantum teleportation does not transmit matter or energy instantaneously. It transfers the information of the quantum state, with the speed of the classical communication as the limiting factor. This process preserves the quantum information without the need for a physical medium to carry it across space. It's a promising method for transmitting information in quantum computing and communication networks. Quantum teleportation has been experimentally demonstrated with photons, atoms, and ions. These experiments confirm the theoretical principles and showcase the potential of the technology. One of the primary applications of quantum teleportation is in quantum computing. It can enable the transfer of qubits between different parts of a quantum computer or network. Quantum teleportation also has implications for quantum cryptography. It can be used to securely transmit encryption keys without the risk of interception. Implementing quantum teleportation requires precise control of quantum states and entanglement. Advances in quantum optics and photonics are crucial for improving teleportation protocols. Quantum repeaters may be used in conjunction with teleportation to extend the range of quantum communication networks. These repeaters help maintain the integrity of entanglement over long distances. The fidelity of quantum teleportation depends on the quality of the entangled pairs and the accuracy of the operations performed. High-fidelity teleportation is essential for practical applications. Research in quantum teleportation continues to push the boundaries of what is possible. Scientists are exploring new methods to increase efficiency, reliability, and distance. Quantum teleportation challenges our classical understanding of information transfer. It demonstrates the unique and non-intuitive capabilities of quantum mechanics. The future of quantum teleportation holds the promise of revolutionizing communication and computing. As the technology matures, it will likely play a crucial role in the development of advanced quantum systems. Quantum sensing exploits quantum phenomena to achieve high-precision measurements. It uses properties like superposition and entanglement to measure physical quantities with unprecedented accuracy. Quantum sensors can detect minute changes in magnetic fields, gravitational waves, and other physical parameters. This makes them useful in a variety of scientific and technological applications. One key advantage of quantum sensing is its sensitivity. Quantum sensors can detect variations at the atomic or subatomic level, far surpassing classical sensors. Applications include medical imaging, where quantum sensors can improve the resolution of techniques like MRI. This allows for earlier and more accurate diagnosis of medical conditions. In navigation, quantum sensors can enhance the precision of inertial navigation systems. These systems are crucial for submarines, spacecraft, and other vehicles operating without GPS. Quantum sensors also have applications in environmental monitoring. They can measure weak magnetic fields generated by geological formations or detect minute changes in atmospheric conditions. In fundamental physics, quantum sensors are used to test the limits of physical theories. They can detect gravitational waves or test the equivalence principle with high precision. The technology behind quantum sensing often involves cold atoms or ions. These systems are isolated from their environment to maintain quantum coherence, which is essential for accurate measurements. Entangled particles play a crucial role in quantum sensing. Entanglement enhances the precision of measurements by correlating the states of multiple particles. Quantum sensing can also leverage squeeze states of light. These states reduce quantum noise, allowing for more precise measurements of optical signals. Developing practical quantum sensors involves overcoming technical challenges. These include maintaining coherence, reducing noise, and integrating quantum systems with classical measurement devices. Quantum sensors have the potential to revolutionize many industries. Their high sensitivity and precision can lead to new discoveries and improvements in existing technologies. Research in quantum sensing is interdisciplinary, involving physics, engineering, and material science. Advances in one field often lead to breakthroughs in others, driving the technology forward. As quantum sensing technology matures, it is expected to become more accessible and widespread. This could lead to new applications and enhance existing measurement techniques. The future of quantum sensing promises to push the boundaries of what we can measure and understand. Its impact will be felt across science, technology, and industry, opening up new possibilities for precision measurement. Quantum simulations use quantum systems to model complex physical phenomena. They leverage the principles of quantum mechanics to simulate behaviors that are difficult or impossible to replicate with classical computers. One major application of quantum simulations is in understanding chemical reactions. Quantum simulators can model the interactions between molecules, providing insights into reaction mechanisms and the development of new materials. These simulations are particularly valuable in condensed matter physics. They help researchers study the properties of materials at the atomic level, including superconductors and magnetic systems. Quantum simulators can also model complex biological processes. This can lead to a deeper understanding of protein folding, enzyme activity, and other critical biochemical interactions. Another application is in high-energy physics, where quantum simulations can explore particle interactions and fundamental forces. This can provide insights into the behavior of quarks, gluons, and other elementary particles. Quantum simulations rely on qubits to represent and manipulate information. The ability to maintain and control quantum coherence is crucial for accurate simulations. Different physical systems can be used for quantum simulations. These include trapped ions, superconducting circuits, and ultracold atoms, each offering unique advantages for specific types of simulations. One of the key challenges in quantum simulations is error correction. Ensuring the accuracy of simulations requires techniques to mitigate and correct errors that arise from decoherence and other quantum noise. Quantum simulations can provide a better understanding of quantum phase transitions. These transitions occur at zero temperature and involve changes in the quantum state of a system, providing insights into critical phenomena. The field of quantum many-body physics benefits significantly from quantum simulations. Simulating the interactions of many particles can reveal new states of matter and exotic quantum phases. Quantum simulations can also aid in optimizing complex systems. For example, they can be used to solve optimization problems in logistics, finance, and artificial intelligence by exploring vast solution spaces more efficiently than classical methods. Research in quantum simulations is advancing rapidly, driven by improvements in quantum hardware and algorithms. This progress is expanding the scope and scale of what can be simulated. Quantum simulators are also used to test and refine theoretical models. By comparing simulation results with experimental data, scientists can validate and improve their understanding of quantum systems. Collaboration between theoretical and experimental physicists is crucial in this field. The interplay between theory and experiment drives innovations and enhances the capabilities of quantum simulators. The future of quantum simulations holds great promise. As technology advances, quantum simulations are expected to tackle increasingly complex problems, transforming our understanding of the natural world and leading to practical applications across various fields. Chemistry and molecular physics are deeply intertwined with quantum mechanics. Quantum mechanics provides a fundamental framework for understanding the behavior of atoms and molecules. The electronic structure of atoms and molecules is described by quantum theory. It explains how electrons are arranged in orbitals and how they interact to form chemical bonds. Molecular orbitals are formed from the combination of atomic orbitals. These orbitals determine the distribution of electrons in a molecule and influence its chemical properties. Quantum mechanics helps explain the shapes of molecules. The geometries of molecules are determined by the arrangement of electron pairs around the central atoms. Spectroscopy relies on quantum mechanics to interpret the interaction of light with matter. Different types of spectroscopy, such as infrared and UV vis, provide information about molecular structures and dynamics. Quantum mechanics also plays a crucial role in understanding reaction mechanisms. It helps predict the pathways and energy barriers of chemical reactions, guiding the design of new reactions. The concept of potential energy surfaces is vital in chemistry. These surfaces represent the energy landscape over which chemical reactions occur, and quantum mechanics allows us to calculate and visualize them. In molecular physics, quantum mechanics is used to study the vibrations and rotations of molecules. These motions provide insight into molecular properties and interactions. The principles of quantum mechanics are essential for understanding the behavior of electrons in solids. This understanding is crucial for developing new materials with desired electrical, optical, and mechanical properties. Quantum chemistry computational methods, such as Hartree-Fock and density functional theory, are widely used to predict molecular behavior. These methods enable researchers to model complex systems and interpret experimental data. Quantum mechanics also underpins the field of photochemistry. It explains how light can initiate chemical reactions, leading to applications in areas such as solar energy conversion and photodynamic therapy. The study of molecular collisions and scattering processes is another area where quantum mechanics is applied. These processes are important for understanding reaction dynamics and material properties. Quantum mechanics provides insights into the properties of transition states. Transition states are critical points in chemical reactions, and their study helps in understanding reaction rates and mechanisms. Advanced quantum mechanical models are used to study complex biological molecules. These models help in drug design, understanding enzyme function, and exploring the mechanisms of biological processes. The ongoing development of quantum mechanics continues to expand its applications in chemistry and molecular physics. It remains a powerful tool for discovering and understanding the fundamental principles that govern the behavior of matter. Condensed matter. Physics explores the properties of solid and liquid phases of matter. It seeks to understand the behavior of complex systems with many interacting particles. One of the key areas of study is the electronic properties of materials. This includes understanding how electrons move through metals, semiconductors, and insulators. Superconductivity is a fascinating phenomenon within condensed matter physics. Superconductors exhibit zero electrical resistance and the expulsion of magnetic fields below a critical temperature. The quantum Hall effect is another significant discovery. It reveals quantized conductance in two-dimensional electron systems subjected to strong magnetic fields. Condensed matter physics also investigates magnetism. This includes studying ferromagnetism, antiferromagnetism, and other magnetic orders in materials. The field explores phase transitions and critical phenomena. These transitions, such as melting or superconducting transitions, involve changes in the state of matter and are driven by thermal fluctuations. Quasiparticles are an important concept in condensed matter physics. They represent collective excitations in a material that behave like particles, such as phonons and magnons. Topological insulators are a recent discovery in this field. These materials have insulating interiors but conductive surfaces, with properties protected by topological invariance. Quantum spin liquids are states of matter with disordered magnetic moments. They do not exhibit conventional magnetic order, even at absolute zero, offering insights into quantum entanglement and frustration. The study of two-dimensional materials like graphene has revolutionized condensed matter physics. These materials exhibit unique properties due to their reduced dimensionality and strong electronic correlations. Strongly correlated systems are materials where interactions between particles play a dominant role. These systems can exhibit exotic phases, such as high-temperature superconductivity. The role of symmetry and symmetry breaking is crucial in understanding material properties. Symmetry principles help classify phases of matter and predict their behavior under various conditions. Condensed matter physics also extends to soft matter, including polymers, colloids, and liquid crystals. These materials have complex structures and dynamics, influenced by thermal fluctuations and external fields. Experimentation in condensed matter physics often involves techniques like X-ray diffraction, neutron scattering, and electron microscopy. These methods provide detailed information about the structure and properties of materials. Theoretical and computational methods are essential for interpreting experimental results. They help model the behavior of complex systems and predict new phenomena in condensed matter physics. Particle physics studies the fundamental particles that make up the universe and the forces that govern their interactions. It seeks to understand the smallest building blocks of matter. The standard model of particle physics is a theoretical framework that describes the electromagnetic, weak, and strong nuclear forces. It includes particles like quarks, leptons, and gauge bosons. Quarks are the building blocks of protons and neutrons. They combine in groups of 3 to form these baryons, held together by the strong force mediated by gluons. Leptons include particles like electrons and neutrinos. Electrons are fundamental to the structure of atoms, while neutrinos are elusive particles that interact very weakly with matter. The Higgs boson, discovered in 2012 at the Large Hadron Collider, provides mass to other particles through the Higgs mechanism. This discovery confirmed a crucial part of the standard model. Particle accelerators are essential tools in particle physics. They collide particles at high energies, allowing physicists to study the resulting interactions and discover new particles. The weak force is responsible for processes like beta decay. It is mediated by W and Z bosons, which are much heavier than other particles in the standard model. The strong force binds quarks together in protons and neutrons. It is described by quantum chromodynamics, with gluons acting as the force carriers. Electromagnetic interactions are mediated by photons. These interactions govern the behavior of charged particles and are described by quantum electrodynamics. Supersymmetry is a theoretical extension of the standard model. It proposes a symmetry between fermions and bosons, predicting new particles that could solve various theoretical problems. Dark matter and dark energy are major unsolved mysteries in particle physics. They make up most of the universe's mass and energy, but their nature remains unknown. Neutrino oscillations have shown that neutrinos have mass. This discovery has profound implications for our understanding of particle physics and the early universe. Grand unified theories aim to unify the electromagnetic weak and strong forces into a single theoretical framework. These theories seek to explain the fundamental interactions in a more comprehensive way. String theory is another approach to unifying physics. It proposes that fundamental particles are not point-like, but rather tiny vibrating strings, potentially resolving inconsistencies between quantum mechanics and general relativity. Ongoing research in particle physics explores new particles and interactions. Experiments at facilities like the Large Hadron Collider continue to push the boundaries of our understanding, aiming to uncover the fundamental nature of the universe. Quantum optics studies the interaction of light with matter at the quantum level. It explores phenomena where the quantum nature of light and its interactions are significant. Photons are the fundamental particles of light. They exhibit both wave-like and particle-like properties, central to the study of quantum optics. The quantization of the electromagnetic field is a key concept in quantum optics. It describes how light can exist in discrete energy levels, similar to the quantized energy levels of atoms. Quantum entanglement is a crucial phenomenon in quantum optics. Entangled photons exhibit correlations that cannot be explained by classical physics, enabling applications like quantum teleportation. Lasers are essential tools in quantum optics. They produce coherent light where the photons are in a synchronized state, useful for a wide range of experiments and applications. Single photon sources and detectors are vital for quantum optics experiments. They enable the study of individual photons and their interactions with matter. Quantum coherence describes the phase relationship between different quantum states. Maintaining coherence is crucial for many quantum optics applications, including quantum computing. Nonlinear optics involves the interaction of light with materials in ways that depend on the intensity of the light. This field explores phenomena like harmonic generation and parametric down conversion. Quantum optics is fundamental to quantum information science. Techniques from quantum optics are used to create, manipulate, and measure quantum bits, or qubits. Cavity quantum electrodynamics studies the interaction of light with atoms or quantum dots confined in a cavity. This setup enhances the interaction between light and matter, useful for studying fundamental quantum phenomena. Quantum cryptography relies on the principles of quantum optics. Quantum key distribution, for example, uses the polarization states of photons to create secure communication channels. Squeezed light is a state of light with reduced quantum noise in one property at the expense of increased noise in the conjugate property. It has applications in precision measurement and quantum information. Optical lattices use interfering laser beams to create periodic potential wells for atoms. These lattices can simulate solid-state systems, providing insights into condensed matter physics and quantum simulations. Quantum optics also explores the quantum properties of light in various states, such as Fock states and coherent states. Understanding these states is crucial for developing new quantum technologies. The study of quantum optics continues to advance our understanding of light and its interactions. It drives innovation in quantum technologies, including computing, communication, and precision measurement, shaping the future of quantum science. Medical imaging utilizes various technologies to visualize the interior of the body for diagnostic and therapeutic purposes. Among these, MRI or magnetic resonance imaging is a powerful tool. MRI employs strong magnetic fields and radio waves to generate detailed images of organs and tissues. It is particularly useful for imaging soft tissues, such as the brain, muscles, and connective tissues. The principle behind MRI is nuclear magnetic resonance. Hydrogen nuclei in the body, primarily in water and fat, align with the magnetic field and emit signals when disturbed by radio waves. These signals are detected and processed to create images. Different tissues emit signals with varying intensities, allowing MRI to distinguish between them. MRI does not use ionizing radiation, unlike X-rays and CT scans. This makes it a safer option for patients, especially for repeated imaging. Functional MRI or fMRI measures brain activity by detecting changes in blood flow. It helps map brain function and is used in both research and clinical settings. Diffusion MRI tracks the movement of water molecules in tissue. This technique is valuable for studying neural pathways and diagnosing conditions like stroke and multiple sclerosis. Contrast agents are sometimes used in MRI to enhance image quality. These agents, usually containing gadolinium, help highlight specific areas or structures within the body. MRI can be used to image virtually any part of the body. It is commonly used for neurological, musculoskeletal, cardiovascular, and oncological imaging. The development of high-field MRI scanners has improved image resolution and reduced scan times. These advancements have expanded the applications and effectiveness of MRI. MRI is also used in conjunction with other imaging techniques. For example, combining MRI with PET scans provides both functional and anatomical information. The ability to obtain detailed, three-dimensional images is a significant advantage of MRI. This capability is crucial for planning surgeries and other medical procedures. MRI technology continues to evolve, with research focused on enhancing image quality, reducing scan times, and improving patient comfort. Advances in MRI are also driven by developments in quantum mechanics and magnet technology. MRI has revolutionized medical imaging, providing invaluable insights into the human body. It plays a critical role in diagnosis, treatment planning, and medical research, contributing to improved patient outcomes. The future of MRI looks promising, with ongoing innovations expected to expand its capabilities and applications further. As technology advances, MRI will continue to be an essential tool in medical imaging and healthcare. Quantum field theory is a fundamental framework in physics that describes how particles interact and fields behave. It merges quantum mechanics with special relativity. Fields in quantum field theory are fundamental entities. Particles are seen as excitations or quanta of these underlying fields. The theory treats particles like electrons and photons as field quanta. Each type of particle is associated with a specific field. Quantum electrodynamics, or QED, is a key part of quantum field theory. It describes the interaction between charged particles and the electromagnetic field. The interactions are mediated by virtual particles. For instance, photons mediate electromagnetic interactions between charged particles. Quantum chromodynamics, or QCD, extends these ideas to the strong force. It describes the interactions between quarks and gluons, which are the fundamental particles of the strong force. In QCD, quarks are bound together by gluons to form protons and neutrons. The theory explains phenomena like confinement and asymptotic freedom. The Higgs field is another crucial component. The interaction with the Higgs field gives particles their mass, as demonstrated by the discovery of the Higgs boson. Quantum field theory also introduces the concept of renormalization. This process deals with infinities that arise in calculations, making the theory predictive and consistent. Feynman diagrams are a tool used in quantum field theory. They visually represent interactions between particles, making complex calculations more manageable. Gauge symmetry is a foundational principle. It ensures the consistency of interactions and underlies the forces described by quantum field theory. The standard model of particle physics is built on quantum field theory. It unifies the electromagnetic, weak and strong interactions into a single framework. Quantum field theory is essential for understanding high-energy physics. It explains the behavior of particles in accelerators and cosmic phenomena. Advances in quantum field theory have led to new insights into the nature of the universe. The theory continues to be a vibrant area of research, pushing the boundaries of our knowledge. Ongoing research explores unifying quantum field theory with gravity. This quest aims to develop a theory of quantum gravity, integrating all fundamental forces into a coherent framework. Quantum electrodynamics, or QED, is the quantum field theory of the electromagnetic force. It describes how light and matter interact. In QED, particles like electrons and photons are treated as excitations of their respective fields. The interactions between these particles are mediated by the exchange of virtual photons. QED was developed in the mid-20th century by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. They shared the Nobel Prize in Physics in 1965 for their work. One of the key features of QED is its use of Feynman diagrams. These diagrams provide a visual way to represent and calculate particle interactions. The theory accurately predicts phenomena such as the electron's magnetic moment and the Lamb shift in hydrogen. These predictions have been confirmed by high-precision experiments. Renormalization is a crucial aspect of QED. It addresses the infinities that arise in calculations, making the theory finite and predictive. The fine structure constant is a fundamental parameter in QED. It characterizes the strength of the electromagnetic interaction between charged particles. QED also explains the scattering of light by electrons, known as Compton scattering. This phenomenon supports the particle nature of light and the validity of QED. Pair production and annihilation are processes described by QED. These involve the creation and destruction of electron-positron pairs from high-energy photons. QED is a gauge theory based on the U1 symmetry group. This symmetry ensures the consistency and conservation laws of the electromagnetic interactions. The theory has been tested to extremely high precision. It remains one of the most successful and accurate theories in the history of physics. QED also plays a crucial role in modern technology. Understanding electron-photon interactions is essential for the development of lasers, semiconductors, and other electronic devices. Quantum loops in QED account for vacuum polarization. This effect modifies the properties of the vacuum, influencing the behavior of particles and fields. The principles of QED extend to other quantum field theories. Techniques developed for QED are used in quantum chromodynamics and the electroweak theory. Research in QED continues to evolve. It inspires ongoing investigations into more complex interactions and the quest for a deeper understanding of the fundamental forces of nature. Quantum gravity seeks to unify general relativity with quantum mechanics. It aims to describe the gravitational force within the framework of quantum field theory. General relativity describes gravity as the curvature of space-time caused by mass and energy. However, it does not incorporate the principles of quantum mechanics. One approach to quantum gravity is string theory. It proposes that fundamental particles are not point-like but rather tiny, vibrating strings. String theory includes the graviton, a hypothetical particle that mediates the gravitational force. The existence of the graviton is a key prediction of quantum gravity theories. Loop quantum gravity is another approach. It attempts to quantize space-time itself, using a framework that describes space as a network of finite loops. In loop quantum gravity, space-time is discrete rather than continuous. This leads to a fundamentally different understanding of the fabric of the universe. Quantum gravity aims to resolve singularities, such as those found in black holes and the Big Bang. These singularities are points where general relativity breaks down, and quantum effects are expected to dominate. One of the major challenges in quantum gravity is the lack of experimental evidence. The effects of quantum gravity are expected to be significant only at extremely small scales, such as the Planck length. The holographic principle is a concept that has emerged from quantum gravity research. It suggests that all the information contained in a volume of space can be described by a theory on the boundary of that space. Black hole thermodynamics is another area where quantum gravity plays a crucial role. The study of black hole entropy and Hawking radiation provides insights into the quantum aspects of gravity. Quantum gravity also seeks to explain the origin and nature of dark energy and dark matter. These components make up most of the universe's mass-energy content, but are not well understood. The search for a theory of quantum gravity drives much of modern theoretical physics. It represents one of the most profound questions about the nature of reality and the universe. Efforts to unify quantum mechanics and gravity may lead to new technologies and a deeper understanding of fundamental forces. The quest for quantum gravity continues to inspire physicists worldwide. Quantum gravity could reveal new insights about the early universe. Understanding the quantum aspects of the Big Bang could provide answers to fundamental questions about the origin of the universe. The development of a successful theory of quantum gravity would mark a major milestone in physics. It would unify our understanding of the fundamental forces and bring us closer to a complete theory of everything. Quantum chromodynamics, or QCD, is the theory of the strong interaction. It describes how quarks and gluons interact to form protons, neutrons, and other hadrons. Quarks are the fundamental constituents of matter in QCD. They come in 6 flavors: up, down, charm, strange, top, and bottom. Gluons are the force carriers of the strong interaction. They mediate the forces between quarks, binding them together inside protons and neutrons. One of the key features of QCD is confinement. Quarks and gluons are never found in isolation. They are always confined within larger particles like protons and neutrons. Asymptotic freedom is another important concept in QCD. At very short distances, quarks interact weakly, behaving almost like free particles. The color charge is a property of quarks and gluons in QCD. There are 3 types of color charge, and particles must combine in such a way that they form color-neutral combinations. QCD explains the structure and stability of atomic nuclei. The strong interaction between quarks inside protons and neutrons holds the nucleus together. Quark-gluon plasma is a state of matter studied in QCD. It existed just after the Big Bang and can be recreated in high-energy particle collisions. The study of hadronization is crucial in QCD. It describes how quarks and gluons combine to form hadrons after high-energy collisions. QCD calculations are complex and often require numerical methods. Lattice QCD uses a grid of space-time points to approximate these calculations and study the properties of quarks and gluons. The strong interaction is much stronger than the electromagnetic or weak interactions. This strength is what holds protons and neutrons tightly together in the atomic nucleus. QCD plays a role in understanding particle interactions at high energies. It helps explain the results of experiments in particle accelerators like the Large Hadron Collider. Glue balls are hypothetical particles predicted by QCD. They are composed entirely of gluons, and their discovery would provide further validation of the theory. Understanding QCD is essential for interpreting results in nuclear and particle physics. It provides the framework for describing the interactions that govern the behavior of most visible matter in the universe. Ongoing research in QCD continues to uncover new insights into the strong force. These discoveries help us understand the fundamental structure of matter and the early moments of the universe. Topological quantum computing is a promising approach to building robust quantum computers. It leverages the principles of topology to protect quantum information from errors. In this model, quantum information is stored in anyons. Anyons are quasi-particles that exist in two-dimensional spaces and have unique properties. The key feature of anyons is their topological nature. The quantum states depend on the particles' paths rather than their exact positions. Topological quantum computing relies on braiding anyons. Braiding involves moving anyons around each other in specific patterns to perform quantum operations. These braiding operations are topologically protected. Small perturbations or errors do not affect the quantum information, making the system inherently robust against noise. This robustness is a significant advantage over other quantum computing approaches. It reduces the need for complex error correction, which is a major challenge in quantum computing. Majorana fermions are potential candidates for realizing anyons. These particles are their own antiparticles and have been observed in certain superconducting systems. Topological qubits are formed by pairs of Majorana fermions. These qubits are expected to be more stable than traditional qubits due to their topological protection. Research in topological quantum computing involves finding suitable materials. Scientists are exploring materials that support the existence of anyons and Majorana fermions. Quantum gates in topological quantum computing are implemented through braiding. This process changes the state of the qubits, performing logical operations. The field is still in its early stages, but there have been promising experimental results. Observations of Majorana fermions and initial braiding experiments are steps toward practical topological quantum computing. Topological quantum computing aims to achieve fault-tolerant quantum computation. This means that computations can proceed accurately even in the presence of certain errors. The theoretical framework for topological quantum computing is well developed. It combines principles from quantum mechanics, condensed matter physics, and topology. Building a large-scale topological quantum computer remains a significant challenge. It requires precise control over anyons and the ability to manipulate them without introducing errors. If successful, topological quantum computing could revolutionize the field. It promises to deliver more stable and scalable quantum computers, capable of solving complex problems beyond the reach of classical computing. The double-slit experiment is one of the most famous experiments in quantum mechanics. It demonstrates the wave-particle duality of particles such as electrons and photons. In the experiment, a beam of particles is directed at a barrier with two slits. Behind the barrier is a detection screen to observe where the particles land. When one slit is open, particles pass through and form a single band pattern on the screen. This behavior is similar to classical particles. However, when both slits are open, an interference pattern emerges. This pattern consists of multiple bands, indicating wave-like behavior. The interference pattern suggests that each particle acts like a wave passing through both slits simultaneously. The waves interfere with each other, creating regions of constructive and destructive interference. If detectors are placed at the slits to observe which slit the particle passes through, the interference pattern disappears. The particles behave like classical particles, creating two distinct bands on the screen. This change in behavior illustrates the principle of complementarity. The wave and particle aspects of quantum objects cannot be observed simultaneously. The experiment highlights the role of the observer in quantum mechanics. Measuring the path of the particles collapses their wave function, altering their behavior. Even when particles are sent through the slits one at a time, the interference pattern still forms. This indicates that each particle interferes with itself, reinforcing the wave-particle duality. The double-slit experiment also applies to larger particles, such as atoms and molecules. This shows that wave-particle duality is a fundamental aspect of quantum objects, regardless of their size. The results of the experiment challenge classical intuition. They reveal the inherent probabilistic nature of quantum mechanics. In the quantum world, particles do not have definite paths. Their behavior is described by probabilities, and the act of measurement influences the outcome. The double-slit experiment has profound implications for our understanding of reality. It suggests that particles exist in a superposition of states until they are observed. The experiment is a cornerstone of quantum mechanics. It demonstrates the need for a new way of thinking about the nature of particles and waves. Understanding the double-slit experiment is essential for grasping the fundamental principles of quantum mechanics. It provides deep insights into the behavior of quantum systems and the nature of measurement. The Stern-Gerlach experiment is a crucial demonstration of quantum mechanics. It provides evidence for the quantization of angular momentum and the existence of spin. In the experiment, a beam of silver atoms is passed through an inhomogeneous magnetic field. The field exerts different forces on the atoms depending on their magnetic moment. Classically, one would expect the atoms to spread out into a continuous distribution on the detection screen. However, the results show discrete spots instead. These discrete spots indicate that the angular momentum of the atoms is quantized. The silver atoms are deflected into distinct paths corresponding to specific spin states. The experiment demonstrates that particles such as electrons possess intrinsic angular momentum, or spin. For silver atoms, which have a single unpaired electron, this results in two distinct deflection paths. This outcome supports the idea that spin is quantized. Electrons can have spin values of +1/2 or -1/2, corresponding to the two spots observed. The Stern-Gerlach experiment also illustrates the concept of superposition. Before measurement, the spin state of an electron can be in a superposition of both spin-up and spin-down states. When the magnetic field is applied, the superposition collapses into one of the two possible spin states. This collapse is a result of the measurement process. The experiment has significant implications for quantum measurement theory. It shows how measurement affects the state of a quantum system, a key principle in quantum mechanics. The Stern-Gerlach experiment is used in quantum computing and information. Understanding spin and its manipulation is crucial for the development of qubits in quantum computers. This experiment also led to the development of techniques in magnetic resonance imaging. MRI technology relies on the principles of nuclear spin and magnetic fields demonstrated by the Stern-Gerlach experiment. It highlights the importance of quantum mechanical spin in the structure of matter. Spin is fundamental to the properties of atoms, molecules, and solid-state materials. The Stern-Gerlach experiment paved the way for further exploration into the quantum realm. It helped establish the field of quantum mechanics as a robust theoretical framework. Understanding the Stern-Gerlach experiment provides insight into the behavior of quantum systems under measurement. It underscores the fundamental differences between classical and quantum physics. The principles demonstrated by the Stern-Gerlach experiment continue to influence modern physics. They are foundational to our understanding of quantum behavior and the development of new quantum technologies. Bell's inequality tests are fundamental experiments in quantum mechanics. They test the principles of quantum entanglement and the predictions of local realism. John Bell formulated Bell's theorem in 1964. It provides a way to distinguish between the predictions of quantum mechanics and those of classical theories based on local realism. Local realism is the idea that physical properties exist independently of measurement and that information cannot travel faster than the speed of light. Bell's theorem shows that quantum mechanics violates these principles under certain conditions. In a typical Bell test, pairs of entangled particles are generated and sent to two distant locations. Measurements are made on each particle's properties, such as spin or polarization. According to quantum mechanics, the results of these measurements are correlated in a way that cannot be explained by local realism. Bell's inequalities provide a mathematical framework to test these correlations. If the experimental results violate Bell's inequalities, it indicates that the correlations cannot be explained by any local realistic theory. Instead, they support the non-local predictions of quantum mechanics. Over the years, many experiments have tested Bell's inequalities using photons, electrons, and other particles. The results consistently violate Bell's inequalities, supporting the quantum mechanical view. These experiments confirm the existence of quantum entanglement. They show that entangled particles exhibit correlations that cannot be accounted for by classical physics. Bell's inequality tests have profound implications for our understanding of reality. They suggest that the universe is fundamentally interconnected in ways that defy classical intuition. The violation of Bell's inequalities challenges the notion of local hidden variables. It implies that quantum mechanics cannot be explained by any theory that relies on local realism. Bell's tests also have practical applications in quantum information science. They are used to verify the security of quantum cryptographic protocols, ensuring that entanglement is genuine and untainted by eavesdroppers. Experimental advancements have improved the precision of Bell tests. Loopholes, such as the detection loophole and locality loophole, have been addressed in recent experiments, making the results more robust. These experiments continue to inspire new research in quantum foundations. They prompt questions about the nature of space, time, and information in the quantum realm. Understanding Bell's inequality tests is crucial for grasping the non-local nature of quantum mechanics. They provide a clear demonstration of how quantum systems differ fundamentally from classical systems. The legacy of Bell's theorem and its experimental tests underscores the strange and counterintuitive nature of the quantum world. It continues to be a cornerstone in the study of quantum mechanics and the quest to understand the true nature of reality. Quantum tomography is a technique used to determine the quantum state of a system. It involves reconstructing the state based on measurements of various observables. This process is analogous to medical tomography, which reconstructs images of the body from multiple X-ray scans. In quantum tomography, the goal is to obtain a complete description of a quantum state. To perform quantum tomography, multiple measurements are made on identically prepared quantum systems. These measurements are then used to infer the density matrix, which represents the quantum state. The density matrix provides a comprehensive description of both pure and mixed states. It includes all the statistical information needed to predict the outcomes of any measurement on the system. Quantum tomography requires a variety of measurement settings. Each setting provides different information about the state, and together they allow for a complete reconstruction. One common approach is state tomography for qubits. This involves measuring the qubit along different axes, such as the X, Y, and Z directions, to gather the necessary data. Quantum process tomography extends these principles to quantum operations. It characterizes the action of quantum gates and processes, providing insight into their performance and errors. The data collected in quantum tomography is processed using algorithms. These algorithms solve the inverse problem of determining the quantum state from the measurement outcomes. Linear inversion and maximum likelihood estimation are two common methods used in quantum tomography. They provide ways to handle the measurement data and reconstruct the density matrix. Quantum tomography is essential for verifying quantum technologies. It helps in assessing the fidelity of quantum states and the accuracy of quantum gates in quantum computing. The technique is also crucial for quantum communication. It ensures that the states being transmitted and received are accurately known and maintained throughout the communication process. Experimental challenges in quantum tomography include the need for a large number of measurements. This is particularly demanding for systems with many qubits or high-dimensional quantum states. Recent advancements have focused on improving the efficiency of quantum tomography. Compressive sensing and other techniques aim to reduce the number of measurements required while still achieving accurate state reconstruction. Understanding quantum tomography is fundamental for developing and validating quantum technologies. It provides the tools needed to probe and control the complex behavior of quantum systems. The future of quantum tomography promises further refinements and applications. As quantum technologies continue to evolve, efficient and accurate state characterization will remain a key area of research and development. Quantum interference and diffraction are fundamental phenomena in quantum mechanics. They reveal the wave-like nature of particles, such as electrons and photons. Interference occurs when waves overlap, creating a pattern of constructive and destructive interference. This pattern depends on the phase difference between the waves. In the double-slit experiment, particles passing through two slits create an interference pattern on a detection screen. This demonstrates that each particle behaves like a wave, interfering with itself. Diffraction is the bending of waves around obstacles and the spreading of waves through slits. It occurs when the wavelength of the particle is comparable to the size of the obstacle or slit. A single slit diffraction experiment shows a central bright fringe with alternating dark and bright fringes on either side. This pattern results from the interference of waves emanating from different parts of the slit. Both interference and diffraction are explained by the wave function of particles. The wave function's amplitude and phase determine the probability of detecting particles at different positions. Quantum interference is not limited to light and electrons. It can occur with atoms, molecules, and even larger particles, demonstrating the universal nature of wave-particle duality. The principle of superposition underlies quantum interference. It states that the total wave function is a sum of the wave functions corresponding to different paths or states. In quantum mechanics, interference patterns can be used to probe the properties of particles and fields. They provide insights into coherence, phase relationships, and the underlying quantum states. Coherent sources are essential for observing quantum interference. Lasers and other sources that emit particles with a well-defined phase relationship produce clear interference patterns. Quantum interference is exploited in various technologies, such as interferometers and sensors. These devices measure minor changes in distance or other physical quantities with high precision. Diffraction patterns provide valuable information about the structure of materials. X-ray diffraction, for example, is used to determine the arrangement of atoms in crystals. Understanding interference and diffraction is crucial for quantum computing and communication. Quantum algorithms and protocols often rely on coherent superpositions and interference effects. The study of quantum interference also leads to fundamental questions about the nature of reality. It challenges classical notions of particles, following definite paths, and highlights the probabilistic nature of quantum mechanics. Experimental advancements continue to explore new regimes of interference and diffraction. Researchers are investigating these phenomena at increasingly smaller scales and higher energies. The ongoing study of quantum interference and diffraction deepens our understanding of the quantum world. These phenomena remain at the heart of many quantum mechanical principles and applications. In this comprehensive guide to quantum mechanics, we've explored the foundational principles and groundbreaking experiments that define this intriguing field. Starting with the basics, we discussed wave-particle duality and how particles like electrons and photons exhibit both wave-like and particle-like behaviors, a concept beautifully demonstrated by the double-slit experiment. We delved into the fundamental principles such as quantum superposition, where particles exist in multiple states at once, and quantum entanglement, where particles become interconnected regardless of distance. These phenomena challenge our classical understanding of the universe and have profound implications for fields like quantum computing and cryptography. The uncertainty principle, formulated by Heisenberg, reveals the intrinsic limitations in measuring pairs of complementary properties like position and momentum. This principle underscores the probabilistic nature of quantum mechanics, where certainty is replaced by probability distributions. We examined the quantization of energy, a key concept introduced by Planck, and how it explains phenomena like blackbody radiation and the discrete energy levels in atoms. This quantization is crucial for understanding atomic and molecular structures and their interactions. Wave functions, the core mathematical descriptions in quantum mechanics, were discussed in depth. These functions provide the probability distributions for particle properties and are essential for predicting and understanding quantum behavior. The Heisenberg picture and the Schrödinger equation offered different perspectives on quantum dynamics, highlighting how quantum states evolve over time. These frameworks are pivotal for solving quantum mechanical problems and for understanding the behavior of quantum systems. We also explored the realm of quantum field theory, which unifies quantum mechanics with special relativity and quantum electrodynamics, which describes the interactions between light and matter. These theories are essential for explaining a wide range of physical phenomena. Experiments such as the Stern-Gerlach experiment and Bell's inequality tests provided empirical evidence for quantum principles and challenged classical views. These experiments highlight the non-local and probabilistic nature of quantum mechanics. Quantum technologies like quantum computing and cryptography leverage these principles for practical applications. We discussed how qubits, entanglement, and quantum key distribution could revolutionize computing and secure communications. Finally, we looked at advanced topics like quantum tomography, quantum simulations, and the quest for quantum gravity, showing how quantum mechanics continues to push the boundaries of our understanding and technological capabilities. If you enjoyed this video, please like and subscribe to our channel for more in-depth explorations of fascinating topics in physics and beyond. Don't forget to check out our other videos where we dive into various scientific concepts and breakthroughs. Thank you for watching, and stay curious.